Thank you. It's a great honor to speak at Aries Observe event. And I'm Haoqin. I'm from VLAA Lab, UC Santa Cruz. And today I'm going to share our latest work, VLAA-Thinker data model training for vision language models with inherent reasoning abilities. So I'll first give some context about AI and multimodal AIs. AI has reached us at large, becoming a widely accessible tool across society. And the integration of multimodality makes them more powerful in understanding this world, as it allows AI models to process content beyond just text, from image, audio, and video, mirroring the way humans perceive and make sense of their surroundings. So in this presentation, I'll introduce our latest work, VLAA-Thinker, a powerful vision language model with inherent reasoning abilities with full training recipe, data, and model released, as well as training insights for building future multimodal reasoning models. So I'll first go back to what people have done to pursue a powerful model, especially language generation models. So let's first go back to the reasoning abilities of language models, which is widely believed to significantly improve model capabilities and has been a long-standing pursuit. For example, on this slide, you can see that by slightly tweaking the input to ask the language model to think step by step before answering, the model performs reasoning before answering and respond to the question correctly. This is more like a very traditional and conventional approach, the chain of thought or COT approach that help a language model, any language model, even they are not with inherent reasoning abilities, to think before giving the final answer, which can help the model to improve the final performance. So from the plain chain of thought or COT, people have started to seek different approaches to tweak their input. For example, by modifying the prompt format for the model to generate more understandable and more effective chain of thought instructions, to let the model to think, to more advanced strategies that leverage like dynamic searching approaches to select which traces is the best for the answer, or some retrieval-based method like RAG. And to the most recent models like OpenCompass O-series and DeepSeek R1, which demonstrate inherent reasoning abilities that can think without any external tools or prompting techniques. And this significantly enhanced the model's performance compared with those non-thinking or conventional language models. And from the release report from DeepSeek R1, we know that if we want a model with inherent reasoning abilities without leveraging any external prompt or tools, we have to integrate the reasoning traces into the model's training process instead of just give like conventional training paradigm that just give the question and the ground truth to the model for training. But the approach of using inherent reasoning now mainly focuses on language only, and lacking the transparency in the training procedure and also transferability to vision language domains and other multimodality domains. So we aim to prompt the detailed training process for building a vision language reasoning model with inherent reasoning abilities, as well as to develop a powerful vision language reasoning system. So this is some backgrounds and research questions here for our VLAA-Thinker. So the background here is that for either language-only reasoning models or some recent vision language reasoning models, they typically use this two-stage training framework. SFT, supervised fine-tuning on the reasoning data to teach the model how to output reasoning tag or reasoning traces before answering, and then use the GRPO or RL algorithm for the to motivate the model to natively thinking. Sorry. So based on this conventional training framework, our research questions here is that first, what are the distinct effects of supervised fine-tuning and RL in multimodal reasoning? And the second one is this two-stage paradigm. Is this two-stage training paradigm truly necessary for motivating large vision language model with inherent reasoning abilities? So initially, we try to implement the model by leveraging the traditional SFT supervised fine-tuning method on vision language region data. So, so before applying the SFT to the model, there is a main problem for current vision language data, is that current vision language data, they only have the image, visual question, and the ground truth. Like I mentioned before, if we want the model, a vision language model with inherent reasoning, the native reasoning ability, we have to integrate the reasoning traces or the thinking pattern into the training data. So what we did is actually quite straightforward. We basically empower the language-only reasoning model, DeepSeek R1, with a pair of eyes by generating the detailed captions using GPT-4 given the input image. And then we feed the detailed caption and the visual question into the DeepSeek R1 to make the language-only model to think and answer the question. And then we use the rewriter to rewrite the model's response to make sure that the model's generations refers to the image itself instead of the caption. And then we use a verifier to verify if the generated final answer aligns with the golden ground truth, and we keep those with had the correct final answer and discard those don't. And this is what our goal here is to prop the two-stage training paradigm for the model. So we use different data for either SFT or RL. So for different data splits, we divide the data based on the criteria that easier examples are for SFT and the harder ones are for RL, because RL has been proven to help models generalize to all of distribution scenarios and can potentially incentivize the inherent reasoning of language models. So our first step is to use the SFT data to train the model using the SFT paradigm. But we found that though SFT can quickly teach the vision language model to think, to respond with inherent thinking patterns, but that kind of thinking patterns is what we call pseudo reasoning, consists of redundant, incorrect thinking traces, which lead to the incorrect final answer. So here's the number that we use two different vision language models, the Quant2 and the Quant 2.5, across two different model parameter size, the 3 billion parameter size and 7 billion parameter size. And we can see from the number that SFT actually jeopardized the model even compared with the base model. And more SFT data, you can see we tuned the model on 25K and 126K SFT data, and more SFT data even jeopardize more of the model performance. Then the second question is, how about RL? As previous works on language have proven that a two-stage training would benefit the model largely in reasonability. SFT first to teach the model how to generate text, and then RL to help to motivate the native thinking patterns. So we turn our focus to RL. It's a specifically GRPO in our setting. It's a training. It's a very popular training framework that has been proven to be effective for the language domains. So we're using RL here. So one key question is that how do we design our reward function? How do we reward the RL algorithm during the model's training? So unlike previous works that only consider verifiable reward that which is a cross-grained reward function that take every task type as one single type of reward, and they use string match or math verifier to verify if the model generated ground truth corresponds to the golden ground truth. So our first belief here is that we should design a more fine-grained reward function specifically for different task types. So here for the verifiable training examples, we divide four different reward functions based on their task type. For digit and MCQ multi-choice questions, we use a string match to see if the model's generations aligns with the ground truth. And for the math problems, we use a math verifier, a latex math verifier, to verify if the generated response corresponds to the ground truth. And for IOU, we just calculate the distance between the ground truth and the generated ones. And at previous GRPO method that have been proven that the verifiable reward could be helpful to motivate the model to think before answering. We also believe that for some open-ended tasks like creative writing or image captioning, we need reward. So for open-ended general reasoning scenarios, we devise a new reward function that leverage an off-the-shelf output-based vision language reward model to give scores given the input image, the visual question, and the model response. And we take the reward model score as the final RL reward. And here's the results under 3 different experimental settings using the RL algorithm and also the SFT, SFT then RL settings. So it's very clear that models that have gone through only RL phases perform the best. And the rest 2 settings, even though they have the GRPO after RL, they still jeopardize the base model's performance and lags far behind the GRPO only method. That is because, as mentioned before, the SFT helped them, though the SFT helped the model to generate thinking tags and thinking patterns quickly, but it typically leads to pseudo reasoning traces consists of redundant, incorrect reasoning paths. So here's the training traces of the reward length and also reward as the training proceeds of models under different experimental settings. So previous beliefs are that reasoning model, if a reasoning model can produce longer responding length, the model generally perform better. So previous believe that longer response length leads to better performance, but in our experiments, it's quite different. So we found that SFT can help the model to gain much longer distance than the GRPO only method, but SFT model generally performs worse than the RL only method. And from the reward function, we can see that at the initial point, the SFT model has a higher initial reward, which means to the reward functions, the SFT model is better. But as the training proceeds, we can see that the RL only model, the model with the blue line, the reward of the blue line consistently improves and even goes higher than the other 2 settings. Because as the training proceeds, the RL is the only method that help the model to learn the native thinking patterns instead of to simply mimicking what the training data tells the model. And here's the final results across 6 very popular vision language reasoning benchmarks. So our 3 billion parameter models ranks the first place under the 4 billion vision language groups on the OpenLM reasoning leaderboard, and our 7B model ranks the second. It's an open leaderboard, and it was tested by the third party, so it's a fair comparison. And we also release everything of how we build the model, the training data, the report. Here is all online. Our 7 billion model weights, dataset, and our report. So finally, I'm Haoqin, and I also work on benchmarking vision language benchmark, vision language reward model, and also vision language efficient training. And we are cooking the VLAA-Thinker V2 with better training data, improved training paradigm, as well as better performance. So that's basically my talk today. Thank you, guys.
Amazing. Thank you. Well done. We got time for 1, maybe 2 questions. Any questions?
Yeah.
You mentioned kind of earlier in your talk the difference between using SFT versus RL. If RL looks like, in the majority of cases, is generally better for helping to explain the vision model, like, is there a reason to use SFT beyond cost, or?
There a reason to use SFT? Yeah, that's a good question. So, so personally, I think SFT is still very valuable. It has its own value for cases that you don't have very very diverse data. And SFT can help the model to quickly to learn the pattern of the training data. And for cases like DeepSeek's R1, their base model don't have the instruction following ability. So the first step they need to do is to empower the model with instruction following ability. And in that case, SFT can perform better than the RL because SFT can help the model to learn the pattern quickly. Yeah, but RL is kind of to incentivize models' internal knowledge to make it to exploit its own knowledge and even explore its own knowledge beyond its knowledge bound. But that's like another topic.